Okay, this is the last quadratic video I will be posting. 6.6, solving quadratic word problems. So some might argue that this is the most difficult lesson of chapter 3, 4, 5, 6, because now you have all of these tools, all of these strategies. We've gone through all of these lessons, and now is the difficult part of knowing what strategy to use and when. So, sorry, I thought my phone shut off, but it did not. I'm going to start just by this little graphic organizer on the cover of the note before we dive into the examples. So there are two different types, for the most part, of quadratic word problems. We're either interested in the optimum value or we're not, okay? So greatest, least, most, highest, lowest. Anytime we hear words like that, we are interested in finding the vertex, okay? So this is a brand new strategy from Unit 6. If we're given a quadratic relation in standard form and we want to go right to the vertex, we complete the square, okay? Now, that's one option. We could also find the axis of symmetry and then plug that back into the original equation. How do we get an axis of symmetry? Well, look at all of these options we have. We can partial factor. We can use the shortcut. Again, that would not be acceptable on an assessment, but that's a great tool to check your answer. We can factor and think about how much time we invested in all of the different strategies to learn how to factor. Or again, another new strategy from this unit, we could use the quadratic formula, okay? So all of these things are involved in finding the vertex. These guys in particular, they don't take us directly to the vertex, but they take us to the axis of symmetry, which then gets us to the vertex, okay? On the other side of the graphic organizer, we have the types of strategies we use when we are solving a quadratic equation, okay? So let's listen to sort of the difference between these two types of problems, okay? If I gave you a quadratic relation that modeled the height of an object being thrown from the roof of a building, if I wanted to know the maximum height of the object, I would use one of these strategies. However, if I wanted to know how long did it take for the object to reach a height of 15, okay? I don't know if 15 is the maximum height. I'm presuming it's not, but when I'm not interested in the max or min, I would use one of the strategies on this side of the graphic organizer. And in all honesty, I could talk and talk about it, but the best way to become familiar with these is to do a million examples and lots of homework questions and daily drills, etc. So I am going to post a supplementary set of questions for just extra review, but especially for those of you that want to take 3U, you really want to make sure you're comfortable with all of these strategies and that you have all of these things in your quadratic arsenal, and you make sure that not only can you execute the skill, but you know which skill to use and when. Okay, so the very first example, okay, again, we have an object being thrown from the top of a building rather, and its path is modeled by this quadratic relation. Okay, so just looking at this, what do I know about this ball? Well, I know that its path models a quadratic relation that has a maximum optimum value because the a value is negative. I know the initial height is 10 because that information is what I get from standard form, but I don't know when it hits the ground and I don't know the max height, okay? So it's really important, without even reading the rest of the question, I think it's good to kind of look at the information you've been given and decide, what do I know? Now, part A says, when will the object hit the ground? Okay, so if they want to know when it's going to hit the ground, that means I'm looking for zeros. All right, so this would have been a question we would have done back in Unit 4 when we were talking about factoring, because factoring allows me to find the zeros. However, my instructions said round to the nearest hundredth, and right there, that tells me it's likely that this guy cannot be factored, and so my new awesome alternative to factoring is to use the quadratic formula, okay? So instead of using x's and y's in the quadratic formula, I'm going to use h's and t's because, again, we're looking at the time to reach a specific height. So t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now I will replace these variables with brackets. Okay, and fill those brackets in accordingly. So B is 8, A is -5, and C is 10. Okay, remember my policy, folks. By the time you get to the third step, I want to see 3 numbers. So this works out to be -8. This works out to be 264. Okay, and on the bottom here we have -10. And then from there, you can take me to the 2, oops, I was going to put X, but I want to use T. You can take me to the 2 final answers. Okay. And again, I would recommend pausing this video and trying these calculations on your own, because if you're not getting the same answers that I'm getting, we want to figure out why before the stakes are a lot higher on a test. Okay, so this works out to be, so if I take -8 minus root 264 equals divided by a -10, I get 2.42 seconds. And if I take -8 plus root 264, press equals, divided by a -10, I get -0.82, okay? And in this example, we know that this will be the time when the object hits the ground, because we can't have negative time. But it makes sense that we got negative time. So what I'd like to do now is just kind of use the information that I've come up with here to start a sketch. Because if you're anything like me, the sketches are always very valuable in understanding what's going on in the question. So we have time in seconds and we have height in meters. And we said at the beginning of the question, we know what the initial height is because we can take that right from standard form. So the object started at a height of 10 meters. Okay, it was released. It had a parabolic path. It makes perfect sense that this parabola opens down again, because the A value is -5. And now we just found that it hits the ground after 2.42 seconds. Now the other 0 was a negative number. And even though we can't have negative time, it makes sense that it was negative because it wasn't released from the ground. It was released from a height of 10. Okay? So this is kind of a nice question because we're using new strategies from this unit. We used the quadratic formula. We did not complete the square because it didn't ask me for the optimum value. It didn't ask me for the max height. It asked me when it hit the ground. Normally, like I said earlier, we would factor in a question like this, but factoring is not going to help me when we have numbers that can't be factored. And that's why the quadratic formula came in handy. Now, the next part of the question says, when is the object at a height of 12? Okay, so part B, let's say 12 is here, okay? Without even solving this question, I know this is awesome. It is 10:25 p.m. and I can hear my kids giggling. Love that. I know I'm going to get 2 answers. It's going to reach a height of 12 once on the way up and once on the way down, okay? And again, the instructions say round to the nearest hundredth, which means I am likely going to use the quadratic formula here. Okay, so let's go back to here, and because of the magic of the dry erase board and marker, I am going to just kind of go on top of what I've already done. So now I am no longer interested in a height of 0. I am now interested in a height of 12, okay? Now, this is a very commonly made mistake on assessments, okay? Kids jump right into the quadratic formula, but we can't do that until this equation equals 0. So I'm actually going to bring all 3 of these terms to the other side of the equation, rearrange, okay. Oh, rats, I wanted to use that. Okay, maybe I still can. And so I have a positive 5t squared minus 8t, and then I've got 12 minus 10, which is a plus 2. Okay, so once again, I'm going to use the quadratic formula. Just some of it is going to change in here. So let's just kind of get rid of some of these. All right, and that, and that, and that. Okay, I probably could have just erased and started from scratch, but whatever. Okay, so this time B is -8. and A is 5, and C is 2. Okay, and remember, write the formula down. Then I want to see you plug into the formula, and then I want to see 3 numbers in the third step. That just makes it consistent and easy for me to mark. So minus a minus 8 gives me positive 8. This gives me, again, be careful here, please. That's negative 8 squared. If you were to do this on your calculator, negative 8 squared, your calculator is going to tell you that that's negative 64, and that's simply not true, right? We have to square that negative also. So that's 64 minus 4 times 5 times 2. We get 24 inside the square root sign and 10 in the denominator. Then by the time you're done the third step, you can break it down. So 8 plus root 24 equals, divided by 10, is 1.29 seconds. And 8 minus root 24 divided by 10 is 0.31 seconds. Both are feasible, which makes perfect sense, because as I said a second ago, this object is going to reach a height of 12 meters once on the way up at 0.31 seconds and once on the way down at 1.29 seconds. Okay? Now, you might come across a homework question where it says how long. So I'm adding this in because I don't want you to get stuck if you see this on an assessment or in the homework or on a drill. If the question had been worded like this, how long was the object above 12 meters? Okay. We would follow all the same steps. The only difference is we would take these two answers and subtract them. So think about it. If it hit 12 meters at 0.31 seconds and stayed until it hit it again, right? We need to figure out the time that's passing between 1.29 and 0.31. So you would just subtract those two. Okay, and what would that be? Again, this was not one of the questions I had asked in the note, but I just want to prepare you in case you come across it. Okay, so we've answered 1A and 1B. Now, in part C, it says, what is the maximum height of the object and when does it occur? Okay, we have all kinds of options here, because if we go back to the very first page of the note, look at all the tools that you can use to find the optimum value. What I'm going to do, just because it's a brand new tool in this unit, I'm going to solve for the maximum height by completing the square, okay? However, as I've said already, there are multiple different tools that you could use to find the max. The only reason I'm going to complete the square is because it's a brand new tool this unit, and it'll give me a chance to review that process. So, I need the original equation if I'm going to complete the square, and I don't have it in front of me. Oh, here it is. Okay. All right, so when we complete the square, we factor the coefficient of the coefficient of t squared or x squared from the first two terms, which means I'm going to divide the first two terms by a negative t. Now, if this divides nicely, we're good. We can work with decimals. However, if it does not, you have to leave it as a fraction. And you know what? Just for practice, let's go ahead and leave it as a fraction. That's nice. I haven't done a video like that yet, so it'll give you an opportunity to see what this looks like. So if I divide 8 by a negative 5, I'm going to get negative 8 over 5t, okay? And then close that bracket up and plus 10. All right, next step, I'm going to recopy what I have. Give myself some room. Now, I'm going to have to erase this in a sec because I'll need the space, but that's fine. So I'm looking at negative 8 over 5. I need to find a half of that, which would be negative 4 over 5. And then I need to square it. Square the top gives me 16, and by squaring the bottom, I get 25. So I'm going to add 16 over 25 and subtract 16 over 25. Okay? And please do not be concerned. It looks ugly because we're working with fractions, but it's the same process we've been using all along. Remember, this guy is the guy that's going to end up inside the brackets, okay? That's kind of the magic number. So in my next step, just gonna leave him here because I'm gonna need him in a minute. Minus 5. Remember, this is a perfect square trinomial. And so when I factor it, I'm gonna get t minus 4 over 5 squared. This bracket is owned by a negative 5, and I'm about to pull out minus 16 over 25. So in order to release him from the bracket, so to speak, I have to multiply those together. A negative and a negative is going to give me a positive, and that works out to be 16 over 5. Again, plus 10, we copy that in every step. And then we're at the last step in this entire process where we collect like terms. So I get negative 5 t minus 4 over 5 squared. And I'm going to use my handy dandy fraction button. And I get 66 over 5. Okay, if it makes you feel better, we can go ahead and convert these to decimals now. So we get minus 5 t minus 0.8 squared plus 13.2. And I love completing the square because I am staring at the good stuff now. This tells me the axis of symmetry. This is when the object reached its maximum height, and this tells me what the max height was. Okay, as I've already said, and if you have the teacher copy of the note in front of you, you could have taken the zeros, added them together, and divided by 2 to get the axis of symmetry and plugged it back in, okay? You could have partially factored. You could have used the shortcut to find the axis of symmetry. Of course not for marks. That technique is only used to check your answer. I won't accept that on an assessment. We have all kinds of things we can do to find the axis of symmetry. I've chosen this method because then it allows me to review our new technique of completing the square. So now that I've got this good information about the optimum value, I want to add it back to my diagram because now the pieces of the puzzle are coming together. I'm starting to get all of the important points of this parabola. So when did this object reach its maximum height? After 0.8 seconds. And what was the maximum height? 13.2 meters. Okay? All right. Is there a part C? That was part C. All right, excellent. We are done that question, and we have one more example to go. And I think it's kind of interesting that this last example falls into this lesson because I don't really think we're going to use any strategies from chapter 6 to solve this question. Or we could actually, but we could also use strategies from chapter 5. So let's go ahead and dive right in. It's one of those area questions. All right. And if you're still tuning in, thank you. I know this video is kind of long. Okay. Find the dimensions of a rectangle that has a perimeter of 60 feet. So this is number 2. The perimeter has to be 60 feet, and the area has to be the biggest it could possibly be. Now, in grade 9, either Mr. Burney or Mrs. Mariani or Mrs. Ryan would have taught you that if you want to optimize the dimensions of a rectangle, you make it a square. We know where this is headed, folks. Now, that shortcut doesn't work well when we have questions where, you know, the farmer wants to divide his yard into 4 equal sections, or he wants to use the side of his house as one of the sides of the fence. So there's definitely ways that we can tweak this question. But if I didn't tweak it at all, the bottom line is I know I'm going to have to make this into a square, and each side length is going to be 15, okay? Ooh. However, if you told me that on an assessment, you would get 1 out of a potential 6 or 7 marks. So we need to make sure we can model this using quadratics. All right. If we're not tweaking this at all, if we just are working with a regular rectangular yard, fence, whatever, we know that the perimeter is 60, and the perimeter of a rectangle is 2 lengths plus 2 widths, okay? I don't want to be working with 2 different variables, so I am going to isolate one of the variables. In this case, they're equally easy, okay? All of these numbers are divisible by 2, so we're not going to end up with anything nasty if we choose to isolate L over W. In order to be consistent with the teacher copy of the note, I'm going to isolate W, which means you come over. So I have 60 minus 2L is equal to 2W. And now I have to divide every term by 2. So I get 30 minus L equals W. Okay, my goal here is to maximize area. Area of a rectangle is length times width. Okay, the length is the length. The width is this. So that was the whole purpose of that, is so that we could only be working with one variable. All right, now, yes, we can from this point set these factors equal to 0. However, I want you to see how Unit 6 could apply to a question like this. So what I'm going to do here is expand and simplify and take this, so 30L, to standard form, okay? And I'm gonna have to continue on another board. In order for this guy to be in standard form, I will have to rearrange that equation. So I get A is equal to minus L squared plus 30L, okay? So all I did was flip those guys around. Now, it is a brand new tool. It's a viable option. So I'm gonna show you how you could complete the square to finish this question if you wanted to use a method other than setting the factors equal to 0. Completing the square tells me I have to factor the coefficient of L squared from the first two terms. In this case, that's just a negative. So if I pull out a negative, I'm going to be left with L squared minus 30L. Normally there's stuff here. There isn't. Perfect. Less stuff to worry about. Now I'm going to look here, okay? If I'm working with the number negative 30, I got to take a half of that, which would be negative 15. And when I square negative 15, I get 225. So I'm going to add 225 and minus 225. Okay? Now, I've created a perfect square trinomial, so I'm going to factor it. And if I'm going too quickly, please refer back to the video on completing the square. I go through that process really slowly. So if this is overwhelming to you, definitely watch that one before you, worry about this one. Now, this guy is owned by the bracket, but I want to pull him out. Okay, there's a negative that's in charge of this bracket. I want to pull him out, which means I have to multiply negative 225 by a positive, or by a negative 1, which gives me a positive 225. And I'm done. Now I'm looking at all the good stuff, right? I know that the length that's going to maximize the area is 15, and the max area itself is going to be 225, and this is feet squared, okay? If they wanted to know both of the dimensions, then we can go back to this formula we had earlier for width, plug 15 in there, and then it becomes obvious that the width is also equal to 15, okay? So I would definitely work on the assigned homework. This is your last opportunity to kind of show me what you know with regards to quadratics, because we're, any of the methods that we've used in any of the units are fair game. And like I said, in addition to this assigned homework, your daily drills are always a wonderful opportunity to practice your skills, in addition to the resources I will be posting along with this video. So make sure you do as many different types of word problems as you can to prepare for your final quadratic chapter test.